Okay, so let's just take this equation, x squared plus 2x plus 6 equals 0. When we solve by the quadratic formula, that yields solutions x equals -2 plus or minus the square root of 4 minus 24, all divided by 2. And I can kind of simplify that to -1 plus or minus the square root of -20 over 2, which simplifies to -1 plus or minus the square root of -5. And of course, the square root of -5 is not a real number. There's no number you can square to get a negative. But we can write the square root of -5 is the square root of 5 times -1. And that's equal to the square root of 5 times the square root of -1. And the square root of -1 is our fundamental imaginary number I. So your solutions are x equals -1 plus or minus the square root of 5 times I. Your solution set is then the set consisting of -1 plus the square root of 5 times I and -1 minus the square root of 5 times I. Now, I stands for imaginary, and imaginary numbers are a huge convenience in solving equations of this nature. And when you get into more advanced mathematics, they make life a whole lot easier. Most people don't get to that stage in mathematics, but we need to talk about this because it is something you can encounter. I'll make an interesting aside here. I just read an article where there's some physicists who have written a paper describing an experiment that could be done that shows that imaginary numbers are necessary, not just for convenience, but they're necessary for describing physical reality at the quantum particle level. So there's really nothing that we have used imaginary numbers for in mathematics that can't be done using real numbers. It's just much quicker and easier if we can use imaginary numbers. But it turns out that there might be some aspects of reality that really require that imaginary numbers have reality. So it's kind of an interesting philosophical thing, but that's all I'll say about it. Okay, so we've got this. Now, if we were to multiply this equation by let's say x minus 3 times the quantity x squared plus 2x plus 6. Well, we would get x times x squared plus 2x plus 6 minus 3 times x squared plus 2x plus 6. And this equals then x cubed plus 2x squared plus 6x minus 3x squared minus 6x minus 18. And when we add all that up, we'll have an x cubed. And then we'll have a 2x squared and a minus 3x squared, gives us x cubed minus x squared, plus 6x minus 6x gives us 0, and then minus 18. We know that the zeros of this function are this and this, because that makes this function 0, which means that the whole thing is going to be 0 because you'd be multiplying by 0. You plug either of these in here, you're going to get 0. So whatever x minus 3 is doesn't matter. You're multiplying it by 0, you're going to get 0. And we know also that it's going to be 0 when x equals 3. Okay, so we know that, but how could we find that if we were just given this? Okay, if I just give you these numbers or this function, and you don't already know that it was in this form, how do you figure it out? So that's a question we're going to try to answer. So how to find the zeros of f of x. If we don't already know how it factors. Well, in other words, the question is, how could we factor this? Answer is, start by finding one factor with a good guess. Then divide, put that in parentheses because you don't know what that means just yet. Okay. A good guess would be a factor of 18. You can see why that might be a good guess if you look back to where that 18 came from. Okay. And you see that we have a -3 times 6. That's where the -18 came from. So that 3 is a factor of 18. If you have a linear factor here, then this number might well be a factor of what you get when you get this number. Okay, so a good guess, we start with a factor of 18. Now there's more to it. If we have a number in front of x cubed, then we might want to do a factor of 18 divided by a factor of x cubed. We'll talk about that, but right now, a good guess here would be a factor of 18. It's a good place to start. It's not necessarily going to work. It might be, if I just write down any old degree 3 polynomial with a cube, a square, and an x and a number, it's very unlikely that you're going to be able to factor it. Most of the polynomials that occur in applications in the real world can't be factored, which makes me a little dubious about why we even talk that much about this, since it doesn't really happen. And that's why we kind of skipped a couple of sections, okay? Because I think it's useless for almost anybody. And if it's not useless for you, that means you're a capable mathematics student you're capable enough a mathematics student that you can go on if you happen to be in a STEM curriculum. Personally, I never saw this, even through graduate school. The first time I saw this is when I taught a stupid pre-calculus course. My school didn't even offer courses as low as pre-calculus, okay? I mean, it's great stuff, but if you're a little more advanced, it takes you 5 minutes to figure it out. So why do we go to all this trouble in pre-calculus when it's a little bit more challenging? My opinion is you leave this stuff until later when people are at a level where they can understand it almost instantly. Nevertheless, it's in our curriculum, and some people think it ought to be for whatever reason, and I could be wrong. Okay, I've never been wrong before, but this might be the first time. Now, okay, so back to this. You see that this is this product, and that this 18 came from multiplying this 3, which is a root of the equation, by this number here. So, good guess, we try a factor of 18. And I use the word factor here. And that isn't quite the right way to say it. And actually, I should have. Okay. I really did want to use factor here, but I want to call this a root. A root of the equation is a 0 of the equation. So I'll say a 0 or a root of the equation. Okay, well, right there are your integer factors of 18. Try 1. Is f of 1 equal to 0? Well, obviously not. Because if you put 1 in here, you get 1 minus 1. Those numbers are too small. to combine with 18 and give you 0. Now, you would also want to try -1. And what I should have said here would be plus or minus a factor of 18, okay? So try 2. Well, f of 2 is x cubed, 2 cubed would be 8, but then it's -4 minus 18. And it's clear that the sum of these numbers is less than 18, so there's no way this is going to add up to 0. Also, we want to try f of -2. And that's even worse. Okay, all these are negative. Clearly, it's not going to give you 0. Okay, so we're going to try 3. Now, 3 is going to work if I've multiplied this correctly, and I checked it out, and it seems pretty clear that it works. We're going to try 3. F of 3, well, we plug in 3 for x, we get 27. Now we're getting numbers big enough to maybe handle that -18 there. Okay, so we got 27, and then minus x squared would be -9. Minus 18, that equals 0. So we say bingo. Okay, x equals 3 is a root. Or a 0 of f of x. Okay, now a little board management here. Okay, I've got one. Put this one down here. I don't have to use that other one. Okay. So this thing has x equals 3 for a 0. So it's divisible by x minus 3. So we divide this by x minus 3. We do a long division. Now notice that we don't have an x in here. We really want to have an x in here. If we're going to have a polynomial of whatever degree, we've got to represent every power of x when we do this. Since we don't have an x, we just write a plus 0x. And clearly this is the same as this. Here we just didn't write out the 0x, and we don't really have to unless we happen to be doing long division or something else that really requires that we have it. Okay, so x minus 3 divides this. Well, x goes into x cubed, x squared times x squared times x minus 3 is going to give you x cubed minus 3x squared. Now, following the procedures that we saw last time, we have to subtract this from this. Now, I could explain all the reasons. And I kind of like doing that, but it's a little bit hard to understand, so it probably isn't something we really want to do. Okay, so anyhow, we put a couple of negative signs in here. Of course, that should be positive. When we subtract these things, we're adding the negative x cubed and a plus 3x squared. If we do then x cubed minus x cubed, we get 0. Negative x squared plus 3x squared is 2x squared. And then we got plus 0x. Now, x goes into x squared, 2x times. In other words, if we put 2x here and multiply it by x, we match that 2x squared. So that we can write a 2x squared down here, and then a minus 6x, because of course 2x times negative 3 gives us negative 6x. Remembering to write down the signs that we would use if we wanted to add these. We now see that the 2x squared goes away, gives us 0, 2x squared, negative 2x squared. And 0x plus 6x gives us 6x. And then we have the minus 18. And the x goes into 6x 6 times, or if you want to look at it this way, if you're going to multiply this by 6, you're going to match this 6x, and you're going to get 6x minus 18. You're going to write the opposite signs down here because you're subtracting. And you see that there's no remainder. So thus, your f of x equals x cubed minus x squared minus 18 equals x minus 3 multiplied by x squared plus 2x plus 6. And now we've discovered what we already knew, wherever it is. I guess I've already taken that board away. Yep. Okay, so what did we start with? We started with x minus 3 times x squared plus 2x plus 6. That's how we got this. But if we didn't know it, this is how we would rediscover it. So we can say that we've rediscovered what we started with. So f of x equals 0. If and only if x minus 3 equals 0, or x squared plus 2x plus 6 equals 0. This has solution. X equals 3, just add 3 to both sides. -1 minus the square root of 5i, because that was the solution we got previously for this quadratic factor. And -1 plus the square root of 5 multiplied by I. Now there's a really big deal. And again, I'm looking at board space. So I got some stuff I don't want to erase. And of course I got a big deal here too, but this is in linear algebra, which is a much more advanced course. Got to have at least a semester of calculus. Take that one. So we don't want to talk about the linear algebra big deal, but here's another big deal. Okay, well, just to start motivating this, notice let me back up a second. X minus 3 is a linear function. So we're going to say that 3 is a linear factor. Really didn't need to write that, but I did, so I'll live with it. Okay, this x squared plus 2x plus 6 is an irreducible quadratic factor. Irreducible because it doesn't have real numbers for roots. It has no real roots. It has only complex roots. And I'll say even more than that. I'll say only complex conjugate roots. Now you know from having done the homework that the two roots you get from the complex, the plus and minus of the quadratic formula, those are conjugate roots, okay? -1 minus this imaginary and -1 plus this imaginary are complex conjugate roots. So I'm going to make sure we understand that terminology by inserting a little more on this board just to make it even messier. So these are complex conjugate roots. Now here's the big deal. Now we got the terminology, because I realized I wasn't going to be able to get the terminology on this board. Okay, big deal. Any polynomial is a product of linear and irreducible quadratic factors. That is, linear factors like x minus 3, and 5x plus 8 would be another linear factor, a linear function if set by itself, and irreducible quadratic factors, that is, quadratics that don't have real zeros. The x-intercepts of the graphs come from the linear factors. Complex number 0 occur only as complex conjugate pairs because that's what you usually get from the quadratic formula. And depending on how you define the terms, we could also say or equal and opposite pairs of imaginary numbers. Now, there's much more we can say about this. This statement is called the Fundamental Theorem of Algebra. Now, I was in my junior or senior, probably my senior undergraduate year, majoring in mathematics, before I had the machinery from what's called an abstract algebra course to prove that this is really true. So it's not going to be on the test. Okay. Now, at that stage with that machinery, it's a fairly easy proof. But and I was pretty well impressed that it required that much machinery to really prove this thing that seems to be kind of obvious if you play around with these things. It's a big deal, proof. But what it comes down to is you can always, I don't want to say you can, I don't even want to say I can always, because for any equation of degree 5 or more, there are equations where it's impossible to figure out what those roots are. Okay. And that came out of the same machinery that we used to prove this. This is an easy proof, the proof that a 5th degree polynomial is not generally solvable is a much more detailed application, complicated application of the machinery. Gets into what's called Galois theory. Well, that's before what you, that's way beyond what you need to know. And this is the real reason why if you have a 3rd degree polynomial, you don't have more than 3 roots. Okay, well, I'm going to say a little bit more around the topic of complex numbers. Actually, we're on the topic of solving equations. Another example. Let's take this. Now, if I expand that, 3x times x squared gives me 3x cubed. 3x times 2x is 6x squared. We have a minus 5x squared. So we get a plus x squared. 3x times 6 is 18x. Negative 5 times 2x is negative 10x. So we get negative 8x minus 30. So this gives us this equation. Now, again, if we didn't know where this came from, how would we figure it out? Well, we have possible rational roots. Plus or minus p over q P is a factor of 30, and Q is a factor of 3. Where do we get the 30 and the 3? Well, the 30 is here, and the 3 is here. If this thing is going to have a linear factor, well, you see that the linear factor, if you set 3x minus 5 equal to 0, you're going to get 5/3. And the 5 is a factor of 30, and the 3 is a factor of 3. So and when I say factors of 30, I'm not writing out integer factors, but I mean whole number factors or integer factors, okay? Factors of 30 are 1, 2, 3, 5, 6, 12, 15, and 30. I don't think I missed any.
Are you sure 12 belongs there?
I'm sorry, let me ask again. Factors of 3 are 1 and 3. Now again, what did you just ask?
12 belongs to the factor of 30?
Yeah, 5 divides into 36 times.
12. Hold on. 12?
12 doesn't go into 30. 12, if you divide 30 by 12, you get 2.5. Okay? We're just talking about the whole numbers, or counting numbers even, that divide into 30. So you could divide it, 4 isn't, because 4 into 30, 4 goes into 32, doesn't go into 30. 5 goes into 36 times, so you get 5 and 6. And I did write 12, didn't I?
That's what I'm talking about, yes.
I don't know why I did that. Again, thanks for paying attention, because apparently I wasn't. Okay. Okay, there they are. Your factors of 3 are 1 and 3. Okay. So guesses, and they aren't really necessarily guesses, they're kind of informed guesses. Could be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, and so forth. All these over 1. Well, plus or minus 1/3, plus or minus 2/3. We could do plus or minus 3/3, but that would just be plus or minus 1. So we won't write plus or minus 5/3. And 6 over 3 is 2, so we already covered that. Plus or minus 15/3, plus or minus 30/3. The last one we get would be plus or minus 30 over 3. All the other numbers you get when you divide these numbers by 3 are just reduced down to these numbers. So that would be kind of a complete list. This one goes on, to 5 over 1, 6 over 1, 15 over 1, 30 over 1. Okay? The really big numbers are probably going to be too big because the x cubed is going to be too big. And you can kind of get a feel for that, but usually want to start with numbers that aren't too small or too big. And sometimes nothing is too small. So we could try 1. And 1 is too small because your -8 and your -30 just kind of overwhelm the rest of the numbers. And this is not equal to 0. And f of -1 isn't equal to 0. So that isn't any good. Now f of 2 is going to be a little more promising. And that's going to give us 24 plus 4 minus 16 minus 30. But no, the minuses are still add up way bigger than the pluses. F of -2 is -24 plus 4 plus 16 minus 30. That's getting a little closer, but not all that close, okay? Actually, it's not all that close. And that's clearly not equal to 0. The negatives are too much bigger than the positives. F of 3 would be 27 plus 9 minus 24 minus 30. Okay. Well, that's -54, but that's only 36. The minuses are still too big. And f of -3 isn't very good. Okay. So then you get to 5, and 5 cubed is 125. And there's nothing going to happen on these numbers that's going to match 3 times 125. And you know what?
I think you lost one.
Yeah. You think what?
I think hold on, x cubed needed to be multiplied by 3
By
again.
3, yeah. I was just seeing the same thing. So what I just said about 125 has to be multiplied by 3, just like this does. Okay, now we already see that the 81 is getting too big for the rest of these numbers. If we go to what I was saying with 5, we're going to get 125, and 3 times that's going to be 375. And there's no way these numbers are going to match 375. So we can abandon the rest of these numbers if we see that clearly. And now if nothing works out, maybe we try them to see if maybe we're thinking wrong, because that can happen. But now we go to plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, and so forth, okay? Now, f of 1/3, well, 1/3 is pretty close to 0. All these numbers are going to be pretty small. It's not going to match -30. So I'm going to say no way. Same with f of 2/3. But now we get to f of 5/3. And as we can see from this factor, that one's going to work. We get from this, we get 375 over 27. And that looks a little ugly, but it's, 13, 14, somewhere around that range. X squared is going to be 25/3. 8x is going to be 40 thirds, so it's going to be minus 40 thirds. And then minus 30. Well, turns out I'm not going to do the arithmetic, but you put all this over common denominator 27. And I'm going to write it out. It's going to be 375 and then we need 9 times 25, which is 225 over 27. And I was wrong about this. That should be 25 over 9. I was careless. So it's going to be a little hard to read if I don't. Do this neatly. Okay, so that's going to be 75 over 27. And then this has to be multiplied by 9, 360 over 27. Then we got minus 30. Well, 30 over 27 is 810 over 27. And I think I've got a sign wrong. These three numerators add up 810. I've got a minus on this one, but the root isn't minus anyhow. That's going to be 0, which means that x minus 5 thirds would be a factor. And then you would recover it. Now, the main thing I showed you here is that these are the numbers you try. And if it isn't a multiple of this divided by a multiple of this, it's not going to work. Still wonder why that arithmetic didn't work out, because I know that has to be right. Did I do something wrong? I got negative 10x, yeah. It's 18. You know what? This should have been plus 8x. So that makes this plus. It makes this plus. And now it does equal 0. Of course, all these 8s here should have opposite signs. They still don't equal 0. And the thinking is similar to what I did. Okay. But I was playing careless here. When I got a negative 8. Okay. 3x times 6 is 18x. Negative 5 times 2x is negative 10x, and that adds up to plus 8x, not negative 8x. Okay, well, that's just the arithmetic of it. It's, I think, really interesting stuff. I think it's really neat. It's not that hard to understand. It's not that hard to understand why it's true. That doesn't change the fact that I think it's useless at this level. That's just my opinion. But this is within the whole idea of complex numbers, because now when you divide by x minus 5 thirds, you get this, and you're going to get another complex solution. Okay. Now I covered that because I noticed that in the homework, some of these problems, the only problems that appeared to give you any trouble were the ones where you had to find zeros. So let's go back and look at a couple of those. all I have to do is figure out where my browser is. There we go. And I have it already pulled up.
Mhm.
So let me take one of the more interesting ones that appeared on the homework. Okay, and this would be f of x equal 4x cubed plus 4x squared minus 13x minus 22. Okay. Your factors of 22 are 2, 11, and 22. Factors of 4 are 1, 2, and 4. I'm going to start with just the integer factors of 22. And I'm not going to list them all. I'm going to pull them out as I need them when I see what's happening with this function. Okay? So, yeah, you also have 1. Okay? 1 is clearly not going to work because you're going to have 8 here, and then you're going to have minus 35 here. Negative 1 might work. So f of 1 is 4 plus 4 minus 13 minus 22. Clearly not 0. The negatives are too big. F of negative 1 is going to be negative 4 plus 4 plus 13 minus 22. And is that 0? Well, you got negative 26 here. You got plus 17. The negatives are still too big. That's not equal to 0. Let's try f of 2. Okay, well, 4x cubed is going to be 32. And 4x squared is going to be 16. And then minus 26 minus 22. I bet this is going to work. We get 48 and minus 48, and that equals 0. So we can say bingo. Okay? Just using this idea. And very often, the factors of this are going to work. Okay? And most of the problems you're likely to encounter, you're not going to have a whole lot of them where you have fractions, because that gets a little messy. We just want to teach the basics here, since we're teaching something worthless in the first place. Okay, it's worthless, but it's really interesting. I love it. So I like to teach it, except that I hate to teach people something that's worthless. Okay. Again, that's just my opinion. There are plenty of people way smarter than I am who have a different opinion. I swear, I think it's just habit, though. Okay. Again, I teach something that's not going to be needed till you get to a much more advanced course, when it would be easier to understand, and I don't know, not that hard to understand. We'll go with it. Okay. So now x minus 2 is a factor. So, well, we divide x minus 2 into 4x cubed plus 4x squared minus 13x minus 22. And incidentally, there's a process called synthetic division where you just write out these numbers and do what you would do for long division. And I think that's just another completely worthless thing to be teaching people, because if you don't understand this, you're not going to understand that. And this is easier to remember than that is. Okay, x minus 2 goes into this and you get 4x squared. And you multiply that out, you get 4x cubed minus 8x squared. Make yourself a little notation. If you got a different color, it's helpful to use that. And to remind yourself that you're going to do 4x squared plus 8x squared, you're going to get 12x squared minus 13x. And then you're going to get, well, you need a 12x here because you got to match your 12x squared when you multiply this by this. Or x divided into 12x squared gives you 12x either way. And then that's going to be minus 24x. And no, I thought I was in trouble, but I'm not. Okay, you get a minus here and a plus here. And then negative 13 plus 22 is 11x. I got 9 there when I did it quickly in my head, and that wasn't going to work. But anyhow, you have 11x minus 22. X goes into 11x 11 times. You get 11x minus 22. Everything works out. Okay, then f of x is x minus 2 multiplied by 4x squared plus 12x plus 11. Is this irreducible or not? I think we get 168 there. Did that too quickly in my head. Now it's 176. Okay, 4AC. Really should slow myself down. At some stage, your brain does slow down a little bit. Okay. 144. And you can plug the numbers in carefully, and I could be wrong on this, but this gives me negative 3/2 plus or minus the square root of 32 over 8, but that's square root of 2 over 2, I think. Okay.
Didn't we leave the imaginary number?
I'm sorry? Oh, yeah, it's imaginary. I get hung up doing too much in my head and then I forget to write stuff down. Okay, so I believe that might be correct. Now I'm going to go back to your problem and see what you got. You got your square root of 2 over 2, but you've got a square root of negative 2 over 2. You got 3/2.
I forgot to do the same thing. Forgot to do the imaginary number.
Yeah. And I think maybe you should have a negative here, negative 3/2. Okay. Now I can actually peek at the solution. And yep, exactly what I wrote down here. So one of your roots is clearly 2. And the other 2 roots are these. Okay, so, okay, you were totally on the right track with that. You're just watching me too much and making the kind of mistakes I do. So you got to be careful who you listen to. Okay, well, that's all the material. We'll talk for a minute. I'm going to stop the recording. I'll